Hi, it's Mr. Bennett here. In today's video we're going to be looking at longitudinal and transverse waves. Right, so let's get into it. Right, so obviously a wave transfers energy in the form of oscillations, and there's two types of waves. Now the first wave that we're going to be looking at is a longitudinal wave, and then we'll be also looking at a transverse wave today. So in a longitudinal wave, we classify those as mechanical waves. And the motion of the particles in the wave is parallel to the direction of the wave. These waves also need a medium to travel in. Now transverse waves are electromagnetic waves, and the motion of the particles is perpendicular to the direction of the wave, and they don't actually need a medium to travel in. So an example of a mechanical wave would be a sound wave, and a transverse wave would be a light wave. They're probably the two classics that we need to look at. Alright, so looking at a longitudinal wave, we call that a compression wave. So we have areas of compression and we have areas of rarefaction in that particular wave. So if you think about playing with a slinky spring, we can set up a compression wave in there where all those springs are compressed there, and you've got areas where there's no compression. Alright, so obviously with that you can see that the particles or the spring coils themselves travel in the direction of the sound wave itself. Alright, so sound waves, the mechanical waves, they travel about 340 meters per second, depending on the air temperature and the density of the air. They need a medium to travel through. Now obviously they'll travel faster through a more dense medium than sort of a less dense medium. So they'll travel much quicker through water, a sound wave, than through air, and obviously through say a metal, they'll travel quite quickly through that. You can't hear a sound wave in a vacuum. Obviously they need a medium to travel through. The particles move in the direction of the wave itself, right? So that's they just oscillate back and forth, and I'll show you a simulation at the end of this video. Humans hear about 20 hertz to 20,000 hertz. Right? Now, obviously, if you're a bit older like me, your top range will probably drop down to about 15,000 hertz. Right, so transverse wave or light waves is an example of that. The movement of the particles is actually perpendicular to the direction of the wave itself. Right, so light waves basically travel at 300,000 kilometers per second, or 3 by 10 to the 8 meters per second. They can travel in a vacuum. Obviously they don't need a medium to travel through. The particles move in a perpendicular direction to the direction of the wave. And different colours obviously they have their own particular wavelength. So the visible light spectrum ranges from about 450 nanometers up to about 750 nanometers. So in this bucket simulation, what we've got here is we've got a wave. I'll just start that again. Right, so we'll go real time. Right, so this wave here, it's got a frequency of 1 hertz. So there's one wave every second, and the speed of the wave is 100 centimeters per second. And we've got an amplitude of 2. So if I just pull that amplitude down here, we'll make that go down to 1. Right. Okay, and what you notice here, this is actually a compression wave here. You notice the particles are moving back and forth in the direction, and you're getting these areas where you've got compression and you've got areas where you've got less particles. So let me increase the frequency of that. And we'll see if we can get a bit more of a pronounced thing. Wave speed. Right, and we'll do that. Right, so you can see quite clearly you've got areas where you've got nice compression and not so. Right, now if I change that to looking at a rope, you can see that the particle itself, we'll just slow that down a little bit. The particle is actually moving up and down perpendicular to the direction of that wave, and that is a classical compression, like a transverse wave. Right, looking at that. So the wave direction goes from left to right and the particles are moving up and down. So I hope in this video you've actually learnt that the difference between a longitudinal wave and a transverse wave. I hope you can understand and know the direction of the particles in the wave themselves. And then I hope you understand that different types of waves will require a medium for them to travel through or not. I think the easiest way for me to remember a lot of that information is generally a sound wave is a longitudinal wave, and any electromagnetic wave, so something like a radio transmission or a TV transmission or light, they are all examples of a transverse wave.